so section 3, exploring real numbers. That's a key word today. Underline it, box it, etc. Because the word real, actually, as we kick off and start, is the fundamental idea of the whole day. A real number. Something you can measure. Something you can do on the number line and put a dot on the number line. Now, we don't have a number line here, but if you imagine a number line with 0 in the middle, and the positives to the right and the negatives to the left, a real number is you could take and put your finger on the number line, assuming it went far enough, for any real number. It's real. You can measure it. Now, in saying it's a real number, and I'm emphasizing the fact that this is a number that you can put on the number line, what am I inferring? That there are numbers that are what? That you can't put on the number line. Now, we're not going to talk about those today. Those are called imaginary. But there's a whole other set of numbers that we're going to learn later in the year that are called imaginary numbers. So today we're going to focus, and everything you've done up so far is a real number. So I want to emphasize that and don't just kind of gloss over the title. Real numbers can be broken into a number of different groups. Have you ever seen the prescription drug sign and it's got like a funny big cursive R and there's like does a little X down here at the bottom? Well, that cursive R is the symbol for all the real numbers. So instead of writing all real numbers as your answer, you can do that big cursive R. Just don't turn it into the drug symbol by making a little X at the bottom. Okay? So that's the big symbol, and that was the best that the computer font could do to the cursive R right there. Now, the real numbers, as we know them, the smallest group, what did you start with? When you started with your mom and dad years and years and years ago, you started with by counting, right? And we said, how many fingers? 9, okay, 1, 2, 4, no, we missed 3 there, okay, back up, 1, 2, 3. And those were the counting numbers. And it was very natural to count that way, and that's why they call the counting numbers the natural numbers. So we no longer call them the counting numbers, we call them the natural numbers. Then, a number of years ago, the Egyptians came up with the need to identify the idea of 0. What do we call it if there's nothing there? And so they came up with the number 0. And so when the number 0 was added, it formed a new set of numbers. It wasn't the natural numbers, it was the numbers that start with the whole. And so they called them the whole numbers. You see how 0 is a whole. Okay? So if you're trying to remember what are the whole numbers, it starts with the whole. Okay? Then, they said, oh, there must be something that's not 0. Then what if we go the opposite direction? And we do kind of the idea of take away and subtraction. What happens then if you have numbers that are not positive? Then you're going to end up with numbers that are negative. And all the numbers that are negative and positive on the number line are called the integers. So you've got 3 big numbers. Now, of those 3 sets, which is the largest? Sarah? The integers seem like they're the largest. However, here's a little trick part. What are these 3 dots in on each one? It goes on and on and on. How far?
Forever.
Forever. Now, you understand that infinity is an idea, and it's not a number. So if infinity is an idea, and it means it goes on forever, then what's bigger? 1 to infinity, or infinity to negative infinity? All the same. It seems like there's more numbers, but in reality it's so large, so immense, the size of the universe that God created, so huge that we can't get our arms around it. And yet his power and his size and his grandeur says he can hold the world in the palm of his hand. So when you think about infinity, think about the grandeur of God and his power and his majesty and capacity. Just a little bit of a taste when we start thinking about infinity, and he always was. Before anything happened, he was, and before anything occurred, and before anything was created that he created, he was. And when all is said and done, he still will be. And we are just but a blink of an eye on earth here before we go live with him in heaven. So, different sets of numbers will need to be able to identify. So if I say something's the number 3, notice how many sets does it fall in? Both the natural and the whole and the integers. So we need to be comfortable identifying numbers and knowing what groups they go in. Then we have a new set. They said it's not enough just to count. What if we divide stuff in half and cut them in thirds and things like that? And they came up with what happens if we write a number like a fraction. Okay, 2/3, 1/2, 1/3, 1/4. Those are all numbers that are called rationals. Now I want you to take the word rational, I want you to underline the first 5 letters. What happens when you underline the first 5 letters of the word rational? What do you get? Ratio. And what's a ratio? Typically we think of that as a fraction. Okay, so a ratio is the root word for rational, and that was how we classify any rational numbers. Notice it can always be written in one simple way. Something where we say a fraction like a over b. And a over b can be any number in here. Any number in the integers. All right? Then you can also write it as a decimal. On your calculator, 0.33333 ... means, what's the ... mean?
Forever and ever.
Forever, it keeps on going. And then a rational number can also be written as a decimal that stops. For example, 1/2 is what decimal? 0.5. 1/9 is what decimal? 0.9. Okay? So you can either write 1/9 as 1/9 or 0.9. Done. So a rational number has 3 parts, and you're going to be asked to bring this stuff back to me, Wyatt. You can write it as a fraction. You can write it as a terminating decimal. What does terminating mean? Stops. Or you can write it as a repeating decimal. 3 ways that a rational number can be written. Those 3. Boom, boom, boom. Put a little note up here that says, this will very likely be on the quiz or the test. This is something that we really should know. Stars, light bulbs, whatever helps you identify that that idea is something that you should review. Okay? Put a note to yourself. 3 big definitions of a rational number. Okay? Now, I wrote all this out. In years past, I've had my students be writing and writing and writing and writing and writing, and instead I wanted to type this out so it was simple and clear and you don't have to get writer's cramp even from scribbling all like that. Now, I like to think of these as the women because they are very logical and orderly and things like that, and me as a guy, I'm typically not quite that orderly and that organized. So I think of myself as the irrational. Because when I argue, I never repeat myself. I always keep trying a different thing to get my point across. Even if it doesn't work, I try a different thing, and then I try a different method, and then I try another different method, and each time I keep on arguing, and I still don't get it, that it's not going to work. And yet my argument keeps changing. And if your argument keeps changing, that's not a very rational way to think. It's very irrational. And an irrational number is the same way as a decimal that doesn't what? 2 things. Doesn't repeat, but then I'm so blockheaded that I don't stop either. Okay? So a decimal number, I want you to write right now, if you can, an irrational number. Go. Write me a decimal that doesn't repeat and doesn't end. Go ahead. Everyone try. Write a decimal that doesn't repeat and doesn't end. Someone give me theirs. What they write? Pi. Ooh, very good. Do you know what pi is, other than the symbol? How does it start? Start it out for me. 3 point. Anybody know any of the digits? Jade? 1 4. Anybody know the rest? Ethan?
159.
Ooh, 159. Anybody know more? Pat?
265.
265. Anybody know more? 358. on and on and on and on it goes. And that's pi. Notice, did the decimals have any pattern? No. But if it was 3.141414141414, is that repeating? So what kind of number would that be? Rational. So decimals that don't repeat and don't add? Irrational. Now, I have some other examples down here. See the square root of 10? The square root of anything is irrational so long as the number you take inside, Hannah, is not like 4 or 9 or 16 or 25 or things like that, because those are perfect squares. But the square root of anything, take your calculator out if you have it handy, punch in the square root of something that is not one of those 4, 9, 16, 25, 36, 49 numbers. Punch it in, and you should get a decimal on your calculator. I'm curious how many decimals your calculator has. Find the square root button there on your calculator?
No.
No? Let's see if we can find it. If you look on your calculator, right here, above the x squared button is the square root button. So if we go second square root 5, close parentheses, enter. Does that repeat? 2, 3, 6, 0, 6, 7, 9, 7, 8. Does it repeat? No. That's irrational. So any square root of a number, so long as it's not a perfect square, is irrational. So that's one way to define an irrational. So it doesn't repeat and it doesn't end. Special number like pi that Ty gave us. Okay? Square root of 10. Now what's special about this one? Can you pick up what's going on here? 0.21, 211, 2111, 21111. Is there a pattern?
Yeah.
But does it repeat? No.
Yes.
There is a pattern, but it doesn't repeat. So that's another way to think of an irrational number. So we have definitions here. Rational, 3 big ideas. Irrational, 2 big ideas. Or actually, just 2 ideas. It doesn't repeat, and it doesn't end. So I will ask you probably what the difference is of those 2 ideas next Friday on the quiz. So I will pretty much lay it out. When I give you an assessment of some sort, it's not going to be a surprise what's on there. So you're going to know and have a really good idea of what's on there. So I tried to put kind of a box down here at the bottom of the sets of numbers. The smallest set is the naturals. And notice that has the smallest box. Then the next larger box is the whole numbers. And notice what whole numbers also include. They include the naturals. Then the next bigger box than that is the integers, and they include the whole numbers and the naturals. And then bigger than that is the rationals, because we can write any one of these numbers as a fraction. And then a different set of numbers down here at the bottom is the irrational numbers. And together the rational numbers and the irrational numbers make up the largest set that we know, which is called the real numbers. So just trying to give you a way to kind of put that in perspective. So Patrick, when I ask you what a number is, you should be able to say, oh, that's part of this set and that set and that set. That's all. All right, so let's flip the page. Bunch of terms I just need to go through very quickly. It's raining. I look outside. Is it raining? No. So I just went outside, it's not raining. That's a counterexample. It's something that proves the statement is false. All right? And inequality, something that relates 2 phrases together that may or may not be equal. These are all examples of inequalities, these 2. You guys know the bigger one goes on the side that's bigger. You've learned that. And the smaller one goes on the side that's smaller. So if I'm comparing the 2 numbers 2 and 6, I'm going to make it that way. Some people used to think of it's the alligator eats the bigger one. You know, that was the back way we used to learn it. Equal to, less than or equal to, greater than or equal to. Now, how did this symbol compare to that symbol? I didn't put them up there. What do we do to it? How does it change? Give me some ideas. Can you barely see it over here on the side? Put a little line underneath. Have you ever seen this one, where it's got a cross through it? Not equal to. What about the squiggly? Approximately or about. So if you round something, use the squiggly equals. And then the straight vertical bars mean absolute value. And the absolute value means the distance away from zero. What's the interesting thing about the absolute value? The answer is always going to come out and be what kind of number, Emily? Positive, yeah. All right, so we're going to need our calculators here on this next step because we need to put some things in order. So if you take out your calculators, if you would, and someone tell me what is negative 2/3 as a decimal? Negative 2/3 as a decimal. What do you get? Go ahead, Emily. Okay, negative 0.6 repeating. You can put a bar over that. That means repeating. Or you can put dot, dot, dot. All right, what is negative 7/12 repeating? Somebody else. What do you think? Negative 7/12. What do you get on your calculator? Emily, go ahead. Okay, negative 0.583 repeating. All right. Can we do negative 3/4 without a calculator? Andrew? Negative 0.75. Now, the question asks us to order these from least to greatest. This would be easy if they were positives. But when they're negatives, it's a little bit more challenging. Now, one thing that often is also helpful is to write them with the same number of decimals. So this has 6 decimals, or 4 decimals. How would I make that second one have 4 decimals? Just add another what? Add another 3. But when Andrew gave me his, he just said 0.75. Done. So if I want to make this have 4 decimals, I need to add what? Ethan? Zeros. Okay. So let's compare them. What is the smallest negative number there of those 3? Is this the smallest? Now remember, smallest means furthest away from 0. Furthest left on the number line. Aiden?
The farthest one to the right.
The furthest one to the left.
Yes, but on
here. Do you think this is the smallest?
The right.
This one?
Yes.
Okay. You think this one is the smallest? Why? Is that the largest number of the 3? And so on the number line, the largest number is going to go furthest to which direction?
To the right.
And to the left. Hello? Yeah. Okay. All right. All right, knock on the door. If no one's there, you can use the garage code. Okay, thanks. Bye-bye. Sorry about that. All right, so this is the smallest. Second smallest, the 0.6. Third smallest, the 0.58. So this third one is closest to 0. I do the negatives first because they're sometimes kind of challenging. All right, let's look at the second one. 22/25. Sorry, why? Go ahead.
They're all equal.
They're all equal? Okay, what? So 22/25, what is that as a decimal?
0.8.
Really? Isn't it just 0.88? All right, now, 8/9 is a decimal. Is that 0.8 repeating?
Yeah.
And this one also is 0.8 repeating. So 2 of them are equal. So how does 0.88 compare to 0.888? 888. Which one's larger? If you're not sure, write them with the same number of decimals. Take the 0.88 and stick a 0 on it. So we're comparing 888 to 880. Which one's smaller? Andrew? Yeah, the 1 plus 8. So this is the smallest, and these two are tied for the largest. So if they ask you to analyze something, Ty, tonight on the homework, the easiest way to do it is to write it as a decimal and write it with the same number of decimals and compare them. If it's negative, it's in reverse order. If it's positive, it's in normal order. Hopefully that's pretty straightforward and not too difficult. So, moving on. To what sets of numbers do the following numbers belong? Let's look at this one first. 0.825. That's a decimal. Does that decimal end? Okay, it ends. It doesn't repeat. So let's talk about what kind of decimal is a decimal that ends. What do we call it? It's rational. All right? It's rational. Now, I'm going to flip over. Within the rational numbers, there's integers, whole numbers, and natural numbers. Is this number an integer? Remember, integers don't have decimals. So is it an integer? No. If it's not an integer, it can't be whole and it can't be natural. So the only set of numbers that it belongs to is rational. Okay? Look at the next one. Is this rational or irrational? It's rational because it ends. Now, is it also an integer? It is. It's also an integer. By the way, notice how many n's does the word integer have? Just one n. Is this also a whole number?
Yeah.
Is it in the set 0, 1, 2, 3, 4, 5? Yeah. So it's a whole number. Is it also a counting number? Is it in the numbers 1, 2, 3, 4, 5? Okay? So this is part of 4 sets of numbers. And the 4 sets would be called like that.
Is there like a word for all 4?
Sorry? All right, let's look at this next one. 0.43, 443, 4443, 44443, dot, dot, dot. Does it end? Okay, it doesn't end. Now, the fact that it doesn't end, Tyler, does that mean it's rational or irrational? Not necessarily. But look at the pattern. Does it repeat? Now, Tyler, what is it? Yeah, it's irrational. Okay, it's irrational because it doesn't end and it doesn't repeat. And that's the key. So therefore, it's irrational. Now let's flip it over. Does the irrational set have any subsets? So that's it. It's just one big group of numbers all thrown together. So it's irrational. So we have one answer, 4 answers, and one answer. Okay? So different numbers are going to have different sets that they belong to. All right, last but not least, let's take a look at some inequalities and equalities and absolute value symbols. Remember, definition of absolute value, if I ask you what it is, what are we going to say? The distance away from 0. So here we have a number, negative 19.01, with an absolute value around that. So how far is negative 19.01 away from 0? 19.01, okay? Which is greater, 19.01 or 19? If you're not sure, write it with the same number of decimals. 19.01, I think, is larger. So what do I call that symbol with the larger one on the left? Greater than. So stick a greater than in there. All right, do B on your own. Compare with your partner. See what you get. Who says less than? Who says greater than? Who's not sure? Who didn't vote? Who still didn't vote? All right. What do you think? Greater than or less than?
Greater than.
120 versus 121. Notice how I added a 0 on there? Why do I add that 0? Because now they both have how many decimals? 3. So this one is like so. And what do we call that? That's called less than.